Hi, my name is Manish Gupta, and in this video, I'm going to talk about the DeepSeek V3 model. Let's get started and let's talk about various aspects. What is the architecture of DeepSeek V3 model, and also go into details about that, and then finally sort of wrap up with how good the model performs, why it is so popular in today's times, right? So what is the architecture broadly of DeepSeek V3 model? Well, it is a 671 billion parameter model, so it's not a small model, and it is basically based on mixture of experts architecture. Although the number of parameters are large, 671 billion, but the number of active parameters per token at inference time is just 37 billion parameters. Um, so it has borrowed several, two interesting architectural innovations from DeepSeek V2, multi-head latent attention and DeepSeek mixture of experts for cost-effective training. We'll talk about details about this on the next slide. Further, beyond that, it has more architectural innovations in terms of auxiliary loss-free strategy for load balancing. Load balancing is really required when you're doing mixture of experts kind of stuff, right? To ensure that none of the experts is really heavily loaded, right? And then it also has this multi-token prediction training objective. Um, Sort of reminds of older models where this multi-token prediction training objective was followed, but then they tried to do it in parallel. This model tries to do this multi-token prediction training objective in sequence, and we'll talk in more details about that. Right? It also has a whole bunch of innovations targeted towards optimized training. Specifically, one of them is FP8 mixed precision training, but then there are other optimizations also that are done for reduced GPU memory usage and accelerated training that I'll talk about in detail later. Right? So for optimized training, it also uses this dual pipe algorithm for efficient pipeline parallelism. So the main idea behind this dual pipe algorithm is to sort of optimize for intra-node as well as inter-node traffic, and then ensure that that communication traffic is nicely overlapped with the computation, so that the computation does not need to wait until the communication is over, and the communication does not need to wait for. So basically, nobody should wait in that senses, and thereby ensure that there is most effective usage of the entire, most efficient usage of the entire cluster. So it sort of hides most of the communication during training through the communication overlap, and also it ensures that there is efficient cross-node all-to-all communication, so as to utilize in the best manner InfiniBand as well as NVLink bandwidths. So InfiniBand is typically used for inter-GPU node communication, NVLink within the node communication between GPUs. So it sort of tries to make sure that this communication is so well optimized that it makes best use of both of those linkages. Okay. Pre-training is done using a massive 14.8 trillion high-quality tokens and diverse tokens as well. Many of these tokens, most of this is from English and Chinese, but they've also tried to diversify. Okay. There is a two-stage context length extension. So initially they pre-train with a small context length of just 4K, but then they extend it to 32K and 128K using yarn. Post-training, well, they actually do both SFT, supervised fine-tuning, and reinforcement learning. More details again later, but then more or less they actually do a long chain of thought distillation of the reasoning capabilities, verification, and reflection patterns from DeepSeek R1 models. Overall, net, the interesting part is that this model, DeepSeek V3, is really one of the best open source models as of now, and very comparable to the best closed source models like GPT-4o, but it is basically trained at a very small budget of about $5.6 million, assuming that there is a cost of $2 per H800 GPU hour. And basically, they use 2.8 million H800 GPU hours for the entire training of DeepSeek V3, including pre-training, post-training, and so on. Okay, so let's get into more details now. Okay, so what is the architecture of this DeepSeek V3 model? Let's talk about MLA and MOE. MLA is basically multi-head latent attention, and MOE is mixture of experts. So mixture of experts is a well-known thing. MLA, it has been around for maybe 3 to 4 years at least. But MLA has been, recently proposed by DeepSeek V2 folks. So let's talk about those. So the model broadly follows, the DeepSeek V3 model broadly follows the transformer architecture, transformer decoder architecture. There's a typical RMS norm. So they normalize before attention and feed forward, which is typically the norm these days. Pre-normalization in that sense is they use RMS norm. So there is a self-attention layer, and then there's a feed-forward sublayer, and so on. Okay, so more or less the architecture is just transformer, and in fact they use 61 transformer layers. Okay, but then there are two components to it. The attention is basically revised as multi-head self-attention, and the feed-forward basically becomes DeepSeek-MoE, right? So what is this multi-head latent attention? Let's try to understand that first. We'll talk about DeepSeek-MoE after that. Okay. So this is the multi-head latent attention architecture block, right? So as you can see, of course, it starts from inputs and then, finally it generates those outputs, and some stuff happens in between. Okay. So in fact, what happens is basically before multi-head attention even occurs. So basically whatever happens is so there is multi-head self-attention still occurring. So that part is still the same. It's just that the way you generate the keys, queries, and values differs. That's the main part. Okay. And in fact, the main part now, how does this generation of keys, queries, and values differ? Well, they basically use the low rank joint compression for attention keys and values, okay, to reduce the KV cache during inference. So the idea is that the KV cache, the key value cache, has to be retained during inference, and that cache becomes very large in size. So as to reduce that size, so as to reduce the size of this KV cache, they basically use latent joint, low rank, joint compression for keys and values. And we will see in detail using these equations just here, how this works. So the input is HT, right? So we start from HT. They basically use this joint matrix WDKV. As you can see, it's basically shared between K and V, so as to basically obtain a latent representation CTKV. Now, those which are highlighted in blue basically are cached for generation. So as you can see, this C is going to be cached, and this is the latent stuff. Okay. Now you can use a key specific weight matrix so as to basically get keys for each of those attention heads. And you can, of course, use a value specific attention metric, a value specific weight metric, so as to basically get the value specific specific value vectors for each of those heads. But as you can notice, it's basically making use of the same CTKV. Okay, so the same CTKV is used at both the places. Okay. Now, of course, for having the position encoding, you basically also compute on top of this HT. You also compute the position representations, and you merge them with the keys for each of those for each of those heads, right? So that basically gives you the overall key vector for the head, and you have the key value vector for each head from here. Now, for queries, you basically don't use the same latent vector, latent matrix, but you actually use a special matrix for queries, just like you typically do in the typical self-attention. And then you essentially, after you get this latent query representation, you use it so as to generate query representations for each of those heads. So the latent representation part is done even for queries, but for caching and so on, KV caches are really important, and therefore that is where it matters more. Okay. Just like you did for keys, you also have a position specific representation for the queries. You concatenate, and that gives you your query vector for each of those attention heads. Okay. So that's the MLA. That's basically the multi-head latent attention. Now let's talk a little bit about DeepSeek-MoE, so mixture of experts. Now in mixture of experts, which has been popular for quite some time in switch transformers, G-sharp paper, and so on, the idea is that the feed-forward network is basically replaced by several expert layers. So multiple parallel feed-forward layers in that senses. Of course, you train many of them. For example, 64 different experts, but then at inference time, when a token comes in, there is a gating logic which decides which of the experts, or well, you pre-decide how many experts you would select out of those 64, but you basically select 1, 2, or 4 select. The gating logic decides which of them to select, and then essentially it forwards the token to only those experts. Okay. Now, how does DeepSeek-MoE differ? So well, they basically have this notion of shared experts and routed experts. So they basically believe in shared experts and routed experts. Now, not all experts are routed experts, unlike typical mixture of experts. Okay, so they have shared experts also. Okay, so there is a whole bunch of these shared experts on the left side that you can see, and then there are also these routed experts that you can see in blue color on in this picture on the right side. So the overall output representation is computed as UT, the input that you pass in, plus the output coming from the shared experts, plus the output coming from the routed experts. Sorry. Okay. So the idea is that now, as usual, as in typical mixture of experts, the routed experts, which experts would be used for routing, is basically decided by the gating logic. So there is a gating logic, typically just a dense layer or a few dense layers, which look at the input UT, and then based on that compute these gate values. Which can be so top k of them are chosen. So top k of them are chosen. In DeepSeek V3, they basically use top 8. So they choose top 8 experts out of 64 so as to essentially decide where should the token be routed amongst the routed experts. However, shared experts are actually used for all tokens. Okay. Now let's look at other innovations in DeepSeek V3 model, auxiliary loss-free load balancing. So when you're using mixture of experts, what happens is that some routed experts may be used heavily while others may not be used at all. And therefore, this is a very common problem. And therefore, people do load balancing by bringing in another loss function. Now, what they do is basically they also come up with the auxiliary loss. They also come up with a way of handling this, but not from a loss perspective. In fact, that is why they call it auxiliary loss-free load balancing. So unlike popular ways of handling load balancing in mixture of experts architectures, where they actually have auxiliary loss, they don't have an auxiliary loss. They do a very simple trick. What they do is to basically, not just use the output, coming from the particular expert, sorry, not just that they use the sort of value, the probability decided about the usage of a particular expert, but they actually also add a factor called BI for every expert. Okay, so basically, SI is basically the gating logic. The typical gating logic would just have SI, which is basically, as you can see, right? It's basically dependent on the current input. So whether a particular expert will be used or not, of course, typically depends on the particular input. Okay, but here they also have this bias BI. And bias BI, now, bias BI is only going to be used for routing. And we'll talk about how this bias BI is calculated and used. But remember, this is only going to be used for routing. When you are essentially going to use this gate value and you're going to multiply it with the FFN output, you see this gate value is going to be finally multiplied by the FFN, the feed-forward network output, as you can see here, right? So this multiplication is still done with the gate value without this dash, in the sense with the gate value without BI. Okay, it's just done based on SIT. Okay. So why is this BI and how is this used, right? So during training, right, which is where this BI is very useful, you monitor the expert load on the whole batch, like you do in typical load balancing methods for a mixture of experts. Okay. At the end of each step, right, you basically decrease this BI by a factor gamma if its corresponding expert is overloaded, right? But if the expert is relaxed, if it is underloaded, then you actually increase BI by gamma. So in general, you basically keep a watch on how loaded this guy is. And depending on that, you basically reduce its load in the upcoming batches in that senses, right? But if the guy is underloaded, you basically try to increase its load artificially by moving around with this BI guy. Okay. Now gamma is basically, of course, the bias update speed. So how fast you respond to underloading or overloading of this model, which they basically tuned and fixed it to some value. Okay. Now they realize that this kind of load balancing helps, but does not really completely, perform as good load balancing as you can expect from a loss. So therefore, they still have a complementary sequence-wise auxiliary loss to prevent any extreme imbalances across routed experts. Okay, so they still have this sequence-wise auxiliary loss, but lesser dependence on that, more dependence on this loss-free load balancing method. Now, one other interesting part about this mixture of experts load balancing is that they do node limited routing. So the idea is that, of course, each node has like 8 GPUs, and there are several nodes in the entire network. Now, when a token comes in, you have to route it to 8 different GPUs, 8 different experts. Okay, and each expert in a mixture of experts typically is loaded on a different GPU. So what if each of these 8 GPUs are on different nodes, right? Which basically means that there's going to be a whole bunch of inter-node communication which is required. And therefore, what they do is to make sure that although they have 64 experts and they choose only 8 of them, but they ensure that they don't send this token to more than 4 experts. So more than 4 nodes. So each token is sent to at a max of 4 different nodes, which house these 8 experts. Okay, and how do they choose these nodes? Of course, they choose this based on the sum of the highest affinity scores of the experts distributed on each node. And then basically they choose those 4 nodes, and then they select the final set of 8 experts where they will get the fully FFN, fully feed forward network computation done. Okay. Now let's talk about the fourth and the most and an interesting innovation called multi-token prediction. Typical multi-token prediction methods earlier, like XProfitNet, basically do parallel multi-token prediction. However, in their case, they do sequential multi-token prediction. So this is their main model on the left side, as you can see, and as it is written here as well. And there is also these MTP module 1 and module 2, denoting basically next to next square token prediction and next cube token prediction. The main model, of course, as usual, does the next token prediction. Okay. So as you can see, these 4 tokens are going in as input T1, T2, T3, T4. The main model's job is to basically predict T2, T3, T4, T5, and then cross entropy loss can be back propagated or computed there and back propagated. Right. The next 2 MTP modules, the multi-token prediction modules, take T2, T3, T4, T5 as input, and then try to predict T4, T5, T3 to T6, and the same thing. And so on, right? So T3 to T6 as input, and T4 to T7 as output. Okay. So the idea is that this multi-token prediction guy has been found to be very useful in previous models as well, because it extends the prediction scope to multiple future tokens at each position, not just the next token, but next to next token and next to next to next token, okay? And so on. You can do multiple such MTP modules. Okay. There are 2 benefits of this. One, it densifies the training signal and may improve data efficiency. So with the same pre-training data, rather than just making one next token prediction, you're making like multiple next token predictions in that senses. And also may enable the model to pre-plan its representations for better prediction of future tokens, and therefore improve the overall accuracy. Okay. Now, as you can see, each of these MTP module has a different architecture compared to the main model. Okay, so each of these MTP modules have an embedding layer and an output head, which is basically very much shared with the main model. So this embedding layer is basically shared across all the MTP modules and the main model. Also, the output head, which basically connects to the vocabulary size layer and predicts the next predicted token, right? In that sense, it's also shared with the main model. Rather than having L different transformer layers as in main model, these MTP modules have only one transformer block. This is not shared. They basically have their own weights. There is also a linear projection layer, as you can see, and then there are these RMS normalization layers. Now, for each of those linear projections, essentially, you combine the representation of the ith token at the k-1 depth and the embedding of the I plus kth token. Okay. So the idea is, for example, in MTP module 1, what you would do is, for example, combine T2's embedding representation from this guy and then T3's representation from this guy, so as to be able to concatenate using this formula, as you can see here, and then do the linear projection represented by the matrix MK here. Okay. Similarly, in the MTP module 2, what you would do is to basically take T3's representation from this from MTP module 1 and T4's representation from MTP module 2, and so on. I mean, of course, you also do it like that. I mean, take T4 from here and T5 from here, and then combine. So you do this position by position combination, and then you basically do linear projection, position by position, but then the transformer block essentially happens all of, combining information across all the positions. Okay. Okay, of course, you compute the loss across all of these tokens at each of those modules, and then overall loss is basically a sum over all of those token prediction losses. Now, DeepSeek-V3 does a whole bunch of training optimizations as well. So it's basically trained on a massive infra, 2048 NVIDIA H800 GPU nodes, each node having 8 GPUs. For intra-node communication, they basically use NVLink, which has 160 Gbps, which allows you to have 160 Gbps communication. Internode is basically done using InfiniBand, which is basically 50 Gbps. So as you can imagine, internode is much slower, about 3 to 3.5 times slower compared to NVLink, intranode communication. Okay. So they perform 16-way pipeline parallelism, 64-way expert parallelism, and 0-1 data parallelism. Now, there are four interesting training optimizations that they do, which I'll talk about. Dual pipe and computation communication overlap, efficient cross-node all-to-all communication, extreme memory savings, right, and FP8 training. So we'll talk about each of them and try to understand, how they work broadly. Okay. So dual pipe and compute communication overlap. I mean, remember, whenever you're working with any parallel processing system, there is always this thing, hey, I mean, can you make the communication overhead smaller so that computation, which is way faster, can actually, can actually keep going without getting blocked on communication. So they do a very awesome job. They divide each processing chunk into four components. One is attention computation, second is all-to-all dispatch, third is MLP, and fourth is all-to-all combined. That's what a transform block really looks like, right? So they divide into four chunks. And especially for a backward chunk, I mean, when you're doing back propagation and so on, both attention and MLP are actually further divided into backward for input and backward for waits. So now these deep level, divisions basically allow them to sort of overlap this computation and communication, overlap the processing being done across these chunks, of course, while respecting dependencies, such that they make the most effective use of the entire system, of the entire cluster. I mean, to be able to also overlap it nicely, they adjust the ratio of the GPU streaming multiprocessors for communication. For communication is to computation ratio. This ratio basically. So overall, they just use 20 GPU streaming multiprocessors. Okay. Now these streaming multiprocessors are really required for communication across GPUs and within the across GPUs within the node and across nodes in a cluster-based setup. Right. So they manually tweak this ratio so as to basically be favorable towards communication is to computation. Also, they ensure that the communication can be fully hidden during execution so as to not really act as a bottleneck at all. Okay. Of course, more details around these are in the paper. Now, the second thing is this efficient cross-node all-to-all communication. Now, which is very much really required when you're doing mixture of experts kind of stuff. First, they ensure that each token is sent to less than 4 nodes, thereby reducing the InfiniBand traffic, so inter-node traffic. When basically the gating logic finishes and it's decided that this token needs to be sent to another node, they basically prioritize that before sending the token to within node GPUs. Okay, so they transmit the token via InfiniBand, of course, to GPUs with the same in-node index on its target nodes. As soon as the token reaches the target node, it quickly forwards via the NVLink linkages to specific GPUs that host those target experts rather than actually waiting for other data transfer to happen. Communications via InfiniBand and NVLink are therefore fully overlapped. So the idea is that whenever the communication is slow, they prioritize that so that basically net the slow communication does not really act as a bottleneck for the fast communication for the fast communications. Now, these fast communications could be either InfiniBand communication or it could also be computation by itself, which is pretty fast in that sense. Okay. The third thing that they do is to perform extreme memory savings with minimal overhead. So to do memory savings, of course, they basically came up with this MLA idea, right? So the multi-head latent attention idea, which basically means that they recompute the RMS norm and the MLA up projection rather than storing it. So they recompute it in the backward pass and thereby save memory there itself. They, as I mentioned, right, they basically only save these blue things, only these latent factors rather than actually storing the normalized as well as the MLA up projected values. Okay. So during training, when you are using learning rate, of course, you decay learning rate over epochs and over batches and so on. So they preserve the exponential moving average of model parameters on CPU for early estimation of the model performance after this learning rate decay. Okay. The third thing that they do is to deploy the shared embedding and output head of all of those MTP modules on the same PP rank. So basically that it's shared as well as also on the same PP rank. So that makes both the embedding computation, the output head computation much faster. Okay, with low memory usage. Okay. Now let me talk about this fourth thing, which is quantization, FP8 training. FP8 inference has been popularly used by several models, but they also do FP8 training. FP8 training faces or any quantized training typically faces challenges because of the outliers that appear in activations, weights, and gradients. So therefore, what they do is to do fine-grained quantization. Fine-grained quantization basically means that you try to reduce the number of parameters on the group of parameters on which you are doing quantization, so that you can come up with very nice buckets, and therefore means of those buckets, thereby reducing your quantization error significantly. Okay. So they do basically two kinds of fine-grained quantization: tile-wise grouping and block-wise grouping. Tile-wise grouping they do for activations, where they basically create 128 size tiles, basically a tile per token per 128 channels. And then they also do block-wise grouping for weights, which is basically 128 cross 128 weights, which basically means one block per 128 input channels per 128 output channels. Okay, so that's that. They cache and dispatch activations so they do mixed precision quantization. They cache and dispatch activations in FP8, but they store low precision optimizer states in bfloat 16. Okay. Now again, when they're using 8 bits, people have tried different combinations of those 8 bits. Of course, one of them is sign bit, but the remaining 7 bits could be 4 exponent and 3 mantissa, or 5 exponent and 2 mantissa. They basically work with E4 M3 format. 4 exponent and 3-bit mantissa. Finally, different deployments at inference time. This is all for training time, but at inference time, they basically have a very different training deployment strategy. At inference time, they have a very different deployment strategy while pre-filling versus decoding. So whenever you basically put up a query, they pre-fill and pre-fill the KV cache and so on, right? So that part is very different from a deployment perspective compared to the decoding part. Again, details are in the paper, but I tried to present an abstract picture here. So overall, what is DeepSeek V3 model architecture? They use they use fully they use this mixture of experts in all of those FFN, so feed forward layers, except for the first 3 layers. Okay? So, and from a shared experts perspective, they have only one shared expert, which basically more or less makes up for that feed forward layer, right? But they also have these 256 routed experts. Sorry, I mean, I think earlier I mentioned they use 64 routed experts, but they actually use 256 routed experts. But yes, they actually choose 8 experts per token, as I mentioned earlier, and each token is sent to less than 4 nodes. Okay. So pre-training, they pre-train on a large 14.8 trillion high-quality diverse token data set, as I mentioned earlier, but the pre-training actually has a very interesting twist to it. They use what is called as the fill-in-middle kind of strategy. So rather than always predicting the next token, they actually take the data set and they try to predict the middle part of a phrase rather than the next few tokens only. Okay, so they basically use what is called as prefix suffix middle framework, where they take the context, the prefix, the suffix, and the middle word is basically what is put at the end. Of course, they still do the next token prediction in that sense, but they do the next token, which is basically the middle part, which was basically kept at the end. Okay. They do multi-token prediction, of course, as we discussed, but besides the exact next token, they actually also predict the next to next token. So they do only one multi-token prediction in that sense, is next and next to next. That's it. Okay. Overall, the model size is 671 billion parameters, of which 37 billion parameters are activated for each token. They pre-train with just a 4K max sequence length, but then they apply yarn, which has become popular for context extension these days, to extend this context length from 4K to 32K and then 128K in 2 stages. Okay. So after pre-training, they do supervised fine-tuning and also reinforcement learning. Supervised fine-tuning is done using 1.5 million instruction tuning dataset samples, where they obtain most of the reasoning dataset samples from R1 series of models and non-reasoning dataset from their DeepSeek-V 2.5 model. Reinforcement learning is actually done using reward models, with 2 kinds of reward models: rule-based reward model and model-based reward models. So for tasks where basically you can actually get deterministic outputs like math coding problems or lead code problems, programming problems, right? You can get the exact output. So therefore, basically the reward is just exact match. While for creative tasks, creative writing and tasks of that kind, they basically use DeepSeek V3 SFT checkpoints, the supervised fine-tuned checkpoints themselves, to define the reward. Okay. They also use group relative policy optimization, as I discussed in the previous video. Their subword embedding is BP based byte pair encoding with 128K vocabulary size. Their entire main model has 61 layers with a hidden dimensionality of about 7,000. So how does DeepSeek V3 perform? DeepSeek V3 performs really well. So as you can see from this chart basically shows you accuracy on the y-axis. Of course, on the x-axis, you basically see several different benchmarks, some MLU benchmark, GPQA, math, AIME, software engineering benchmark, code forces, and SWE bench verified benchmark. So this DeepSeek V3 base is currently the strongest open source based model, especially in code and math. The chat version of this DeepSeek V3 model, which is basically obtained after SFT and reinforcement learning, is comparable in performance, if you compare it with GPT-4o and Claude 3.5 Sonnet. Okay. For each of those benchmarks, you can see there are these 6 models being compared: DeepSeek V3, DeepSeek V2.5, Quen model, Llama model, GPT-4o, and Claude 3.5 Sonnet model. Okay. So on tasks like MMLU Pro, and GPQA, DeepSeek V3 actually is better, as you can see from these bars, right? It's better than open source models like Llama. It's also equivalent in comparison to GPT-4o and Claude Sonnet. On simple QA and Chinese simple QA question answering benchmarks, DeepSeek V3 is clearly better than open source models. It is worse than GPT-4o and Claude Sonnet for these question answering benchmarks for English, but it is better in Chinese. Now, they have a sure bias towards actually pre-training data more on Chinese. Okay. Live code benchmark, DeepSeek V3 is the best, and DeepSeek V3 is actually better than O1 preview on Math 500 benchmark. So that's why it's actually so popular. So in summary, in this video, I talked about DeepSeek V3 model. It's basically a mixture of experts large language model with 671 billion total parameters and 37 activated parameters trained on 14.8 trillion tokens. So nicely, rigorously pre-trained. It basically carries over the innovations from DeepSeek V2, MLA, and DeepSeek-MoE, right? So, but also comes up with new innovations like auxiliary loss-free strategy for load balancing and multi-token prediction training objective. From a engineering optimizations perspective, they've done several optimizations, FP8 quantization, and overlapping the communication and computation nicely, and also ensuring that the mixture of experts basically behaves in a very, very interesting manner, right? So essentially, so as to optimize the overall efficiency of the entire cluster. They basically were able to pre-train this entire model, which actually performs comparable to GPT-4o with 2.8 million H800 GPU hours of capacity of compute, right? For its full training, including pre-training, context length extension, and post-training, all of them. Right now, it's basically the strongest open source model and comparable to GPT-4o and Claude 3.5 Sonnet, especially the chat version. Okay, that's it for this video. Hope you enjoyed the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.